everyone. Today we're gonna be doing more partial fractions. This time it's in the special case of if you have a fraction px over qx, the degree of px is smaller than degree of qx. All that means is, like, for example, if you have the integration of, like, let's say x cubed over something like x to the 4 plus something x cubed, right? Plus something x squared plus something x plus c. You see how this x cubed is smaller than this x4. So when you do long division, right, you're going to end up with x minus 1 on here. You don't want that. So the previous partial fractions kind of method that we did last time, we did it only for the situations for which we can divide by long division. But in this case, we can't divide by long division. And so how are we going to do the partial fractions? Because something like this, that's basically impossible to integrate. So how are we going to decompose it into something that we can integrate, right? And so we're going to do a few examples, and I'm going to show you this theorem. I don't know what it's called. I wasn't told what it's called in class, but I'm going to show you what it looks like. So first, let's do this one. This example here. This is the integration of 2x to the 5 plus 1 over x squared multiplied by x squared plus 1 squared, right? It's horrible. It's absolutely horrible. And I think for every example except one, which is this one, because this is the simplest one, this one here, this is the simplest one. I'm gonna solve it from start to finish. But for these two at the start, I'm going to just give you the example and show you how the theorem works. This one is a trick question. You're going to see how it goes later. So anyways, let's go back to this. So we basically want to represent this. Remember how, when we had let's say we had like x over x squared plus 1 is equal, or like x over like x plus 1 is equal to like x plus 1, x minus 1, like something like this, and we're like plus b x minus 1, right? This is something similar, but it's a little bit more nuanced. So basically, let's get to I just gotta check. Okay. So anyways, I went to check something just because I was a bit unsure, but I'm going to show you how this goes. So let's decompose this equation down a little bit, right? So when we have something like this, we can think of it, the theorem says like this. If we have an expression like this, we can rewrite it. I'm going to rewrite it like this, and you'll see why. All squared, right? The way we can rewrite this equation is simple. It's similar to the other way. We can rewrite it as a over x, right? This x goes here. Plus b over x, because this other x here goes here. Plus c. Now this, I'm gonna backtrack this, but I'm gonna show you what happens. C. Actually, I'll show you. I'll just show you what it is, and then we'll talk about it later. So then we have cx plus d over x squared plus 1. And then we're going to go ex plus f over x squared plus 1 squared. This is crazy, right? You look at this and you go, what the hell is going on? Because first of all, I mean, having this x goes here, this x goes here, and maybe like one of these going here, that made sense, right? That's the first question I saw when I had this. But why do we have this already, right? We have x squared plus 1 already. There should only be another x squared plus 1 before it turns into this, right? We only need another one. Why do we have x squared plus 1 all squared? How does that work? So to answer that question, it's just the way it is. So for example, if you had any function, it seems to, except when it's x by itself, but when it's like a function within a function, it's a kind of like chain rule thing that happens with this kind of theorem, where you just have to do it n times. So for example, this thing is x squared plus 1 to the power of n, and this time n is equal to 2. And so what happens is you have to do it x squared plus 1 to the power of 1, and then do another time when it's x squared plus 1 to the power of 2. So n times. You have to do it 2 times. And it's just the way the theorem works. I'm personally not sure, and I haven't looked through the proof for this yet, but apparently the proof explains this. So that's the idea. Unless it's x by itself, if it's like another function within a function, and it's like to the power of like something, like to the power of n, then you have to do it n times in the denominator that and you increase the power each time. So because we have x squared plus 1 all to the power of 2, then we do x squared plus 1 once, but then because it's power of 2, we need to do it a second time, where it's now x squared plus 1 to the power of 2. Okay, so that's the reason why we're doing this. What the hell is this, right? We understand that it's a over x plus b over x. That makes sense, right? That's what we've done before. But why cx plus d? Why ex plus f? There is no specific kind of rule that says we have to use cx plus d or we have to use ex plus f. We're doing this for convenience. And I'm going to explain to you exactly how it works for convenience. But what we have to understand is when we rewrite a function as ax over x and plus bx over x as a over x plus b over x plus whatever, that's also for convenience. We can rewrite this function in like infinite different ways. We just need to do it for the way that is most convenient for us. And so this is the most convenient way, and I'm going to explain why it's the most convenient way. So let's say that you have the integration of this whole thing, right? The integration of this whole thing. Well, the integration of that is going to be the integration of this whole thing, right? Which we can split up into the integration of a over x dx, x dx, plus integration of b over x dx, plus the integration of cx plus d, cx plus d over x squared plus 1, and dx, and plus the integration of ex plus f to over x squared plus 1 all to the power of squared dx. So this is mathematically true, right? We set the left equation here to be equal to something, and then we say it is equal to this. Therefore, the integration of the left expression has to be equal to the integration of the right expression. Right now, we're mathematically true. So let's try to do this slowly. We have a over x dx, right? What's the integration of that? That's pretty simple, right? Because that's simply the integration of a ln x. Same thing. This integration is very simple. It's going to be b ln x. Therefore, we really like this style where it's just like basically 1 over x and it can be multiplied by something, right? But we like it being 1 over x because the integration of 1 over x is simply ln. Okay. How would you do the integration? Let's say we didn't have cx plus d. How would we do the integration of x squared plus 1 over x squared plus 1? It's tough, right? It's not easy. The reason why we do cx plus d is because we can use u substitution on this. Let's say that we let u, and if we had to do this in an exam, this is what we do. We say we let u equal to x plus x squared plus 1. Therefore, du would be equal to 2x. 2x dx, right? This means that d would be 0, and this here would just be cx would be in this case 2, and cx dx, then that turns into what does that turn into? The integration 2 dx turns into du, so there's nothing left on the top, and now that's 1 over u du, right? It's very, very nice. This is just going to be equal to ln u, and we can sub u in back. So that's the reason why we do this. Same thing over here, right? We have ex plus f over x squared plus 1 all squared. Now, let's say that let u equal x squared plus 1, therefore du equals 2x dx. And we do the same thing, so now f is 0, and that integration here is going to be equal to e is 2, so that's 2x, so let's say that's 2, and then dx, all of that multiplied out, so that's just 1 over u squared, right? Or technically this is u du over u squared, which is actually just 1 over, yeah, it's just this. 1 over u squared du, right? That's the reason why we want to set this equation in a way that is convenient for us. it is convenient for us. And let's say that instead of this, let's say you had a over x plus b over x, but instead of x squared plus 1, you have like over x squared plus 2x plus 1, right? We still gonna use cx plus d, because if we take u equals x squared plus 2x plus 1, well, du is simply 2x plus 2 in the same form as cx plus d. And so now you see the reason for why we set these numerators in the way that we do. The whole thing here, what we're doing here, equating it to some random a, b, c, d, is just for our convenience. And this is also for our convenience, simply because we want it in the form of 1 over u, or 1 over u squared, where we can just simply integrate it into ln. Does that make sense? So yeah, that's the trick. That's the trick that we're trying to do here. This is the kind of, once you get the philosophy of what's going on here, then you can really apply this to the different questions. So now that you understand that, first of all, there's this rule here where you have to do it n times. If it's 2 times, then you have to do it 2 times power of 1 and then power of 2. And then the other idea is how we use this expression for convenience whenever the denominator is like a squared polynomial, like x squared, ax squared plus bx plus c. That is going to differentiate. If we do u equals that, right? U equals that, then differentiation is going to be equal to in the form of cx plus d. That's why we use that. Okay. So once we figure that out, it becomes quite simple, because then you can just, and I'm going to show you how you find a, b, c, d later, and then you can do it. It's not as simple as I put it out, but it's basically among the lines of just trying to get everything in the form of ln, right? But yeah, so later on the easier example, I'm going to show you guys how we're going to find a, b, and c, and d, and that kind of stuff. Okay. So, and the only one where I'm going to do it A, B, and C, and D, like find those, is going to be this one, because these ones are a bit complex. They're not going to be on the test, and so I'm not going to do those. But let's practice our skills, like practice being able to equate it with this equation here. So let's try this. So what we have, I'm going to copy this over. Let's see what this says. So we have x cubed plus x squared plus 1 all over x multiplied by x minus 1, x squared plus 1x, and x squared plus 1 all squared, right? What a horrible equation. So how are we going to equate this to anything, right? Let's forget the integral sign for now. Let's equate this. This equation is going to be equal, first of all, we have an x here, right? A over x. We don't have to do ax plus c. Ax plus b is because x is only a first degree polynomial. So when we let u equals x, well, du is simply 1. Right? So we don't have to worry about any like ax plus b. Same for x minus 1. When we let u equals x minus 1, du is simply going to be 1. Again, or whatever the constant of x is. If it was like 2x plus 1, it's going to be 2, right? But it's not going to be 2x plus something. It's just going to be 2. Therefore, we only need to use b for this one. Okay, now for this. X squared over x plus 1 plus x squared plus x plus 1. Now this one, if we were to try to integrate it using substitution, u equals x squared plus x plus 1, what is this going to turn into? Du is going to be 2x plus 1, right? In the form of cx plus d. And therefore, the one we want to use here, a, b, cx plus d. Okay. Next one. Now we have 2, right? We have 2 of these, 2 of x squared plus 1s. So the first one, remember, if we have it to the power of 2, we have to do it 2 times with ascending powers, right? The first time is going to be only the power of 1, and so it's going to be x squared plus 1 to the power of 1, which we can ignore, right? And so this is going to be, now what's going to happen if we differentiate this? It's going to be 2x plus, obviously it's going to be 0 because there's no x term, but it's still going to be in that general idea where it's going to be ex plus f, right? And so that's what we use. Any second degree polynomial, we have to use this for convenience. I mean, you don't have to, but it's going to make your life a lot easier if you use that. And finally, as the rule states, we're going to go again to the next power, x squared plus 1 to the power of 2. And again, the same form, this time it's just going to be u squared, but the differentiation of u is still going to be in that form. So this is going to be gx plus h, a, b, c, d, e, f, g, h. Okay, yeah. So you see the idea of you can see the interplay of that. And once you're able to kind of lay this equation out, all you have to do is find A, B, C, D, E, F, G, H. And then you're going to be able to solve it using integration of each one. And it's a lot simpler, right? Okay, so let's get back. Let's go do a real example. Let's do a real example where we're going to find A, B, and C, and D and stuff. Okay, so let's do this question. The integration of 1 over x cubed minus x. Okay. So first thing, let's decompose this equation. So this is going to be 1 over x of x squared minus 1. Okay. If you notice, this is the difference of two squares, right? Difference of two squares. It basically means that like a minus b multiplied by a plus b is going to be equal to a squared minus b squared. And so in this case, we have x squared minus 1. 1 is the square of 1, and x squared is the square of x. So we can rewrite this equation as 1 over x multiplied by x minus 1 and x plus 1. Okay, if you notice here, right, there is no second degree polynomial. And so we won't end up with that form where it's like bx plus c or cx plus d. We're just going to end up with like a single constants on top of the fractions, which is why we're going to use this as the example, because it's a lot simpler. Okay, so we can rewrite this equation as, let's see, so this is x, so then this is going to be a over x. Next, we have a over x. Next, we have x minus 1, and so it's going to be plus b over x minus 1. And then we have x plus 1. So we're going to have c over x plus 1. Perfect. Okay. Now, let's give a scenario where we multiply the whole side. We multiply everything by the very denominator, right? We multiply everything by x minus 1, x plus 1. Right? Well, on the left side, 1 over x minus 1, x plus 1, multiplied by the very denominator, that's going to cancel out to be equal to 1, right? Okay, now a multiplied by x, a multiplied by x minus 1, multiplied by x plus 1. But remember, a is on top of x. Therefore, the x cancels, and we end up with just simply x minus 1, x plus 1. Same story happens with b. b is already on top of x minus 1, and so we cancel out x minus 1. It's simply b x plus 1. Same for c. c is already over x plus 1, and so we cancel out x plus 1, which gives us c x, and then x minus 1. Okay. All right, now the trick is, remember from the last video that I made, we're going to compare coefficients, right? Think about this. This equation on the left, we can also assume that it's actually equal to, and it is equal to this, 0x squared plus x plus 1, right? A second degree polynomial with no second degree x, like it's just 0x squared. But look at here, right? We can multiply these out and find the coefficients in terms, coefficient of x squared, coefficient of x. This is 0x. So coefficient of x, and then the coefficient of the constant, which is just a constant. So we can compare the coefficients and then find the values of a, b, and c. And you can also do the thing yesterday where we were like, let x equals 1 and let x equals whatever. So that also works, but I find that the coefficients reduce a lot easier, and when you do the let x stuff, the simultaneous equations are a lot more complex. So we're simply going to be doing this. So if this is going to be equal to, let's get everything out first. So let's multiply these together. So that's going to be x squared, right, plus this is actually the difference between two squares, so all we're going to get is x squared minus 1, right? This is x minus 1 multiply x plus 1, difference between two squares, it's x squared minus 1 squared. Plus b, this is going to be x squared plus x, and this is plus c. This is going to be c multiplied by x squared minus x. Okay, so now let's look at this. So for the x squared coefficients, right? So we looked at all of these. What are the coefficients of x squared? We have ax squared plus bx squared plus cx squared, right? They all have an x squared. Okay. Therefore, it's going to be a plus b, right? Ax squared, or we can just, I'll show you this long version once, and I'm going to do the short version later. Ax squared plus bx squared plus cx squared, and obviously there's a lot more, but we only care about the x squared coefficients for now, is equal to 0x squared, right? Right? If we look at only x squared, 0x squared equals ax squared plus bx squared plus cx squared. You cancel all the x squared out, 0 is equal to a, b, c, right? That's the idea. So what we're trying to do is we're equating the coefficients. So now let's say, because we know it's ax squared plus bx squared plus c, so a plus b plus c is equal to 0. Okay, next equation. Let's look at the constant, right? Constant is equal to 1. A minus a. Okay, a multiplied by minus 1 is minus a. And no other constants, because they're all multiplied by x or x squared, which means they're not constants. So the only constant term is going to be negative a, and negative a is equal to 1. And therefore a is equal to 1. So this is our first solved equation. And next, let's look at the x coefficients. So we got a doesn't have multiplied by x, so a isn't part of the x coefficient. B multiplied by x, so that's b plus c minus x multiplied by minus x, which means c is a negative coefficient, and the coefficient of x on the left side is going to be 0. So 0 equals b minus c, and therefore c is equal to b. Okay, and the final thing left is we got to sub it into here. And so now we have 0 equals, let's rewrite it, 0 equals a plus b plus c. Okay, what's a? A is equal to negative 1, sorry, because 1 equals negative a equals negative 1. So a equals negative 1. B is, let's keep b itself, and then c is just equal to b. Let's say b plus negative 1 plus b plus b. That's going to be 0 equals negative 1 plus 2b, and therefore 1 is equal to 2b, and therefore b is equal to 1 over 2. And since c equals b, therefore c is equal to b, where it's also equal to 1/2. And so we have our coefficients, a equals minus 1, b equals 1/2, and c also equals 1/2. So when we end up with this is, let's rewrite the equation 1 over x plus 1, x minus 1, equals to a over x. I rewrote this in the wrong order. That's going to be unhelpful. So we have a over x. So a is minus 1, so we have minus 1 over x plus b. So what's b? B over x minus 1. So we're going to do b is 1/2. So it's going to be 1 over 2 multiply x minus 1. All right. And then c is also 1/2. So it's plus 1/2 x plus 1. And therefore, these are all the equations. And if we were to integrate this, we'd have to integrate each one of this, which is simply the integration of 1 over x, or negative 1 over x, plus the integration of 1 over 2 x minus 1, plus the integration of 1 over 2 x plus 1. And this is incredibly simple. This is going to be minus ln x, right? This is going to be 1/2 of ln x minus 1. And this is simply going to be 1/2 of ln x plus 1. So you can see kind of the value in which, and how valuable it is to be able to turn it into a form where it's just going to be ln, and it's a lot easier. Okay, so final thing, as a trick question, let's look at this, right? This, okay, the reason why it's going to be a trick question, you're going to see. How are you thinking we should do this? How are we thinking we should do this? So apparently, maybe we have to take this as x, okay, x minus 1, all of that. But then we realize that actually, this down here is the third degree polynomial, right? It's a third degree polynomial. If we expand this out, it's going to be, first of all, let's look at the square. So that's x squared minus 2x plus 1 multiplied by x. And now it's going to be x cubed minus 2x squared plus x, right? So actually, these are going to be the same degree. And so you can actually do long division. You don't have to do, what's it called? You don't have to do the theorem here where we've been doing, because makes doing like when it's px and qx, and when q is a larger degree, right? Qx degree is larger than the degree of px. That makes it possible, because when it's not, it's just a mess, and it's horrible to do. So the theorem helps us do that, makes it possible. But when we can, it might be better just to do the long division method or the division method and then work out the remainder. Okay, so let's think about this then. We're trying to look at the integration of x cubed plus 1 over x cubed minus 2x squared plus x. Okay, So we can do long division, right? We can do long division where it's x cubed plus 1, and it's x cubed minus 2x squared plus x. And I'm going to do it out because I want to show you the idea, but I'm going to show you a shortcut later. Okay, so this is here, so we need to multiply by 1 because then we just want to minus just this expression here multiplied by 1, which is simple, so it's just x cubed. The same thing. Let's write this out with all the slots. Okay, and this is minus 2x squared, yep, and then plus x, and that's it. Okay, so x cubed minus x cubed, that's 0. 0 minus 2x squared. Minus is plus. 0 plus 2x squared is going to be plus 2x squared. 0 minus x, that's going to be minus x. And the 1 goes down here, it's going to be plus 1. And therefore, the answer is going to be 1 with a remainder of here, right? If you remember, when we have p over x, px over qx, it's going to give us a polynomial or some kind of function plus the remainder over qx, the original denominator, right? And so what we're going to have here is we see that the complete division is 1, so there is actually one full division in there. And so our fraction here, x cubed plus 1 over x cubed minus 2x squared plus 1 plus x, sorry, minus 2x squared plus x is going to be equal to the full division, Lx. In this case, Lx is 1. Lx is only 1, but sometimes it has x in it, most of the time. And then now that's plus the remainder. The remainder is this. Remainder is that. So there's 2x squared minus x plus 1 over the denominator, which was x cubed minus 2x squared plus x. Okay? And simply from this on, you could then do the theorem, but it's a lot simpler and it takes out another factor of kind of like having, now you're not doing x cubed, you're doing x squared and that kind of stuff. It's a lot simpler. But okay, what's another fast way? So I'm not gonna do the theorem because we know how to do the theorem already. You have all the rules. I just want to show you a quick way to do this division that Professor Gupta just showed us today in class, and it's really interesting. So this is x cubed plus 1 minus over 2x squared plus x. How do we quickly divide? Because I'm lazy, I'm lazy. What we could do is we could add 0 to this equation, right? When we add 0 to something, it doesn't change, right? It doesn't change. The mathematical value of it does not change, but the form of it does change. The same way that when we change the form with the theorem, it's to be convenient. This is another way to make it convenient. Let's try this. You see that we have x cubed here, right? But then there's this, right? So what we could do is we could say x cubed, okay, plus whatever this is, right? We want to have that in there, plus x cubed, plus x cubed, and then we want to just add this at the back, minus 2x squared plus x. And obviously, if you plus, let's say you plus 10, but if you want to plus 0 in the end, if you plus 10, you got a minus 10, right? Because these cancel out and gives you 0. You don't want to change the equation because that's cheating. We only want to morph it a little bit, but it's the same thing. So then we got to minus the exact thing that we plus. We minus 2x squared plus x, minus 2x squared plus x. And then obviously don't forget the 1 here. So we keep our original equation, right? So this right here, this is 0. This right here is 0, and it does not change the equation at all, right? But what it does allow us is to do something very interesting. So we have this, 2x squared, x cubed minus 2x squared plus x. So what we can do is we can split this function into half. X cubed plus minus 2 squared, so let's minus 2x squared plus x, so plus x over x cubed minus 2x squared plus x. And on this side, obviously, we're going to be minusing this over that. So it's going to be minus 2x. Let's just say it's plus 2x squared minus plus x. That's just minus x. And then plus 1, sorry, over x cubed minus 2x squared plus x. Well, look at this. This is just by itself, right? This is something by its own thing. So like x over x is going to be 1, right? 1 plus 2x squared minus x plus 1 over x cubed minus 2x squared plus x. And look at that. It's the same idea. So if you ever got like a really hard equation to do long division with, you could just try to cheat it and just do it this way. And either way, it's going to give you the right answer. Yeah. So anyways, thank you guys so much for watching this video. I was really confused in class, but now I feel a lot better of it, especially this explanation of, like Linux, I erased all of it. Wow. But Linux, the whole idea of using Linux, that kind of stuff. So it's really cool. Thank you guys so much for watching. See you guys another time. Thank you so much.